end of day. And I was wondering if anybody had any questions about homework number 4.
Question 34.
Oh, you got it. Let's see. Course content, homework 4, edit, question 34. Okay, so question 34 is a K-map. And let's see if we can do that. And what we'll do is so I'll try and keep the colors consistent. Alrighty then. It says here, given the following K-map, find the minimum sum of products. What do I do? Any ideas?
Can you loop the middle 2 rows? Like 4,
Yes,
5?
yes, you can. Let's loop them. And what product term does that correspond to?
D.
Yep, that's exactly right. Let's change colors. What else can I loop?
Can you also loop the elements all in the middle? So like
You bet. Let's do that. And what do we call that product term?
wouldn't that just be B and D? Or sorry, just B.
It's just B. So F equals B or D. Is that the answer? Yes, it is. Actually, what it says is F is equal to D or B. But it's the same thing. What do you think of that? So, is that all right?
Yep.
All right. Any other questions about homework 4? No questions? Well then, I think what I'll do is I'll introduce to you the basic ideas behind steering logic. Steering logic is a reference to multiplexers and demultiplexers, also called encoders and decoders. Let's take a look at what one of these looks like. This is a diagram which you might see in figure 4.28 on page 182. So I'm just going to put page 182 over here. And we're going to use a selector input. We'll call it selector 0. And then we'll have an output, and we'll describe that as F. And what we'd like to do is we'll write it this way: S0, input 1, input 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And here's F. That looks good. So what we'll do is we'll divide this truth table up into two sections. In this one, S is equal to 0, S0 is equal to 0, and in this one, S0 is equal to 1. Now, if S0 is equal to 0, F will be equal to input 0. So we just write input 0 right here, 0, 1, 0, 1. If S0 is equal to 1, then F is going to be equal to input number 1. And we'll write that here. Input 1 is 0, 0, 1, 1. And that allows us to create a truth table with a function. And the function says the output F is going to be equal to the selector input inverted S0 prime ANDed with input 0 or S0 unprimed ANDed with input 1. Now, in case that confused you because I used S0, I1, and I0, I could write it again as ABC. And if I did that, I could put in a K-map, and you don't have to worry about getting confused about the labels. And then we got, we're going to number this truth table. And then we see F is going to be a 1 for 1, 3, 6, and 7. And otherwise it's 0. And now if we want to loop, we can loop in here. And what do we get? A prime C. And we can loop in here. And we'll get A prime B. Is that right? Looks all right to me. So this is supposed to be A. That's input 1. That's input 0. So if C is input 0, then, oh, I see, that's supposed to be S0. Then what we have is, yeah, did I do this right? Let's just make sure. So if S0 is, yeah, we copy, and S1, and we copy it over. So what do I get? A prime C or A prime B equals F, which I can write in the original notation, where A is equal to S0, so that's S0 prime times I0, or S0 prime times I1. Boy, that surely doesn't look right to me. 0, 1.
I think you messed up on the graph with like the AB side, like 0, 0. And then it should be like
0, 0, 0, 1. Oh, yes, 1, 1, 1, 0. Ah, he doesn't know how to do his K-maps. What kind of digital design professor is this? Oh, no. That's terrible. 0, 0, 0, 0, 1, 1, 1, 1, 0. Ah,
All good, Professor.
yes. Sorry, what was the question?
I was just saying it's all good.
It's okay? All right, thank
Yeah.
you. Yeah, so that would mean that this is, I was going to say, how come that didn't work? Oh, there, that's better. So now we take this part out. Good. And this becomes a 0. And that is matching that. which is what you wanted. So in effect, we have built, using a K-map in our functional specification, the 2-to-1 multiplexer, which is cool. That's cool. That's cool. We could do this again, only this time maybe we could do it correctly. Pat, do it correctly. And I think what I'll do is I'll build a 2-input multiplexer. And so we'll build, we'll call this is called a 2-to-1, because there's 2 inputs, which give us 1 output. What I really want to do is I want to increase it. I want 4-to-1. But that's tough, right? Because why? Because let's not do 4-to-1. How about if we do? Yeah, if I do 2, and here I gotta have 4-to-1. A 4-to-1 multiplexer. Not only do I have 4 inputs, but I gotta have a selector. So what we'll do is we'll run it like this. Input 0 through input 3. We'll call this a 4-to-1. The output will give as Z, and then the selectors will be A and B. Now, if I was going to do this with a truth table, kind of be a bit of a bummer, really, because the truth table will have to have 2 to the 6 rows. So that's 64 rows, and that's too much for my little iPad. But one thing I can say is it's going to be M0 times I0 plus M1 times I1 plus M2 times I2 plus ... M sub I times I sub I. And M0 is going to be represented by A, B, prime, prime. And M1 is going to be, right, because you've got 0, 0, 0, 1, 1, 0, and then you can go 1, 1. So what we'll do is we'll have plus A, B, I1 plus A, B, I2 plus ... until we get to A, B, I3. Right? And now what we can do is we can generalize this such that what we're really doing is we're using the selectors to decide how to route the input to a given output. And that's a multiplexer. And you can build these for integral powers of 2, 2-to-1, 4-to-1, 8-to-1, 16-to-1. I don't think you'll find any 32-to-1s in the shop, but they do exist. So you have integral powers of 2, 2 to the n, where n is equal to 0 through infinity. You have ginormous multiplexers. If it's infinity, it's very big, because that's what infinity is. It's just really big. What do you think of that?
So
That's
I have a question. So what are the
Sure.
what are the selectors here? Are they like
They are little product terms right in through here. And so when this is coming up as 0, 1, that has a decimal number equivalent of 1. And what it says is input 1 will be routed to the output. So whatever this is, a 0 or a 1, it'll be routed to the output. And you can see that over in here. So when S0 was 0, input 0 was routed to the output. And so we just copied input 0 over to the output. But when s was equal to 1, then input 1 was routed to the output. And so we just copied that over to the output. We copied input 1 over to the output. And so the selector enables us to choose which input to use. And building it from the K-map should have been trivial, except I screwed up the labeling. But normally it's trivial. Now we do the same thing with a 4-to-1. And if you like, we could do it for an 8-to-1.
Okay, thank you. That helps.
Sure. Somebody's drawing on my picture.
I have a, what is this? I'm just
What
putting
is
arrow
that?
to
This is a
yeah.
list. This is a Mux Size List. So you can build muxes like here. It says you can have a 2-to-1 mux or a 4-to-1 mux like you see up there, or you could build an 8-to-1 mux. 1, 2, 3, 4, 5, 6, 7, 8. And to do 8-to-1, you need log to the base 2 of 8 inputs to control it, A, B, C, because 2 to the 3 is 8. And so that'll take 8 inputs and multiplex them into a single output. And certainly you could do a 16-to-1, but then you'd need 4 inputs for selectors. And if you wanted to do 32-to-1, you'd need 5 inputs. How does that grab you? Does that make any sense?
Kind of.
Kind of?
Yeah.
Well, here, let's take a look. We'll do another one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Here's the inputs for my 16-to-1 multiplexer. Okay. How many selectors do I need? How many selector inputs do I need? I'm numbering these 0 through 15. So there are 16 inputs, including 0.
Oh, okay, I see it now.
I need more selector inputs, right? So I got A, B, C, and D, right? And if I wanted to, I could select A, B, C, D, prime, prime. And what would I be selecting if I wrote this? Well, this is equal to 1, 1, 0, 0, which is equal to input 12. So I'd multiply this by input 1, 2, and I'd know I'd only see input 1, 2 on the output Z if and only if the combination of A, B, C, and D were 1, 1, 0, 0. And so that's how I would design my my 16-to-1 multiplexer.
Why did it need the C and D for the 16?
Because you need 4 variables in order to select for one of 16, because log to the base 2 of 16 is equal to 4, because 2 to the 4 is equal to 16.
So the 4 would just need A and B.
Yeah, if you were just going to do a 4-to-1, you only need A and B.
Okay.
But if you were going to do an 8-to-1, you'd need A, B, C, right? Because 2 to the 3 is equal to 8. Then you could choose one of 8 inputs. I don't know how many that is, but let's pretend it's 8. There's 4, and here's 16. And surely, if I wanted to do 256-to-1, I would need 8 inputs, because 2 to the 8 is 256. If I could draw 256 lines on the iPad, I would, but I can't. That's because it takes too long. Take the rest of the semester. So that wouldn't be good. So that's what you call the multiplexer, or what is sometimes called the mux, and other times it's called the encoder. And those are two terms which are interchangeable, encoder and multiplexer. And so the multiplexer takes many inputs and makes one. So this goes many to one, many to one. That's what a multiplexer does. What do you think of that? So let's relate it to channels, right? Here's the TV with the silly rabbit ears. And now here is a channel encoder, right? Here's CBS, NBC, ESPN, some other junky network thing. I'll call it junky network thing, JNT, the junky network thing. Everybody will want to watch JNT. And so you use the decoder, right, to choose which of these inputs gets routed to your television. It's your channel changer, right? Lets you choose, but how do you control it? Well, you got to have control lines in here, which essentially allow you to choose which channel to pick out. So there, I've related it to something you can all understand, watching television. How's that? Does anybody watch television anymore? I guess you guys all watch YouTube like me, right? Well, maybe you remember watching television. I think you do anyway. So anyways, that's how I relate that. It's kind of a, how do you call it? A selector. That's what it is. It's a selector. You can use that, selector. Selector, C-S-E-L-E-C-T-O-R, selector, there, selector. It lets you select one of the inputs. That's what a multiplexer does, and it's described in grave detail in chapter 4 under programmable and steering logic. And that's what you got. What do you think? Is it clear?
Yeah, I get it now. Thank you.
You got it? Okay, that's great. Thank you.
I'm sorry for writing on the board.
Oh, no, don't be sorry. It's totally fine. Totally fine. So let's think about the dual of the multiplexer. The dual of the multiplexer is, if you have an encoder, the dual must be the decoder. So the decoder, what does that do? So the decoder takes one input and makes many outputs, right? So it does the opposite. So this is a 1 to 2 decoder, and then we'll do another one over in here. We'll do a 1 to 4, and then we'll do another one, 1 to 8, and then we can envision having the selectors here being mentioned right over in here, because it's always going to have a single enable input. Always. And so what we'll do is we'll say this is 1 to 2. Here it is, we'll call it 2 to 4 because we're using 2 selectors. We mentioned it right there. Here we'll call it 3 to 8 because we're using 3 selectors over in here. And if we wanted to do 4 to 16, we could do that with an enable. So that's the decoder, also known as the demultiplexer or demux. So there you have it, the demultiplexer. So I can take a demultiplexer, and this is cool. And what I can do, I'll do the 3 to 8 decoder, right? And what we'll do is we'll write 0, 1, 2, 3, 4, 5, 6, 7. And we'll select with A, B, and C. And what we'll do is we'll use an enable over in here. And now what comes out over here is M0 through M7, where M0 is A, B, C, all inverted. And what that means is that when you put in 0, 0, 0, it'll assert output 0. If you put in 0, 1, 0, that asserts output 2. If you put in 1, 0, 0, that's going to assert output 4. And so now what you've got is all of the product terms available to you for your use. What does that buy you, you ask? Very good question, I say. When you have access to all of the product terms, you can bust them. Bust them out. 1, 2, 3, 4, 5, 6, and 7. And then you can run them into an OR gate. Call it a function and make the connections with any of the product terms you like. And the function will have a canonical sum of products, which is equal to an indice list of all the places where you had a tap. So if that's 1, then it would be 1, 4, and 6. And then if you wanted to tap again, make a new function and call it 0, 1, 2, 4, and 6. In fact, you can make 2 to the n different functions. Where n is the number of output lines. So if I've got 8 output lines, 0 through 7, I can do 2 to the 8 or 256 different possible functions. All I need to do is wire up the connection. And here's the cool bit. If you're programming an FPGA, that's the field programmable gate arrays, in your lab using Quartus, you can make and break these connections and build your own little functions using the Altera Cyclone processor. So in other words, you have an opportunity to build complex function tables using Altera and the FPGA in your DE2 boards. What do you think of that? Slick, right? Very slick. Yes, Professor Lyon, so slick. Super slick. So now you know about decoders, and you know that they have all their product terms. Let's see what happens when you use a practical decoder. Practical decoder. We'll use a 2 to 4 decoder called the 74139. You can find this in the stock room too. So here is a 2 to 4 decoder with selector inputs A and B, and his outputs are inverted. Oh no, what do we do? Outputs are inverted. 0, 1, 2, 3. And you got an enable. So I take the outputs which are inverted and I add my little AND gate and I write F. Find F in canonical sum of products shorthand notation. Abby Bull, what do you think?
I was writing it down. I
Okay.
didn't get to look at it.
What do you think about taking a stab
Do
at?
you mind saying the question one more time?
Yeah. How do you get canonical sum of product shorthand notation for the given circuit? The decoder output is inverted. And it's being run into a Nand gate. Let's take a look at this Nand gate. How would you write out the Boolean algebraic expression for the Nand gate?
Is it A plus B?
Yeah, it's X and Y inverted. Suppose you wanted to use De Morgan's theorem on X and Y inverted. What would you get?
You just get x inverted plus y inverted.
That's exactly right. Thank you. So then if you know that, then this must be equal to X and Y going into an OR gate with inverted inputs. It's equivalent because here we have an OR gate with inverted inputs. And so if you know the outputs are inverted and you know this is equivalent to an OR gate with its inputs inverted, then the inversions cancel. And so what you're really getting is a sum of products form. So you can write it as normal, 1, 2. That's because of De Morgan's theorem. That's because using De Morgan's theorem, we form an equivalence between a Nand gate and an OR gate with inverted inputs. And if the outputs are inverted, then in principle, we need do nothing. Just use the Nand gate as a summing junction. And we have to do it that way because many of the decoders have inverted outputs. For example, the 74139 shown on page 195 has inverted outputs. So to make things work properly, you need to do something to invert those outputs, and you do that with a Nand gate, because the Nand gate is an OR gate with inverted inputs, because of De Morgan's theorem. Okay, now, who's confused?
So was my answer supposed to be 1, 2?
Yep. Yep, that is exactly right. So that's a nice practical application. You can build any function you like using a canonical sum of products and a decoder with enough outputs, assuming you have, if you have a 2-variable function, you're going to need 2 variables for selectors. If you have a 3-variable function, you need 3. If you have a 4-variable function, you need 4. But having said that, it's entirely possible to build arbitrary functions, large functions, using the decoder. What do you think?
I have a question about it.
Sure.
So you know how next to the 2:4 you have the 0, 1, 2, 3. Is the fact that it's like equal to the binary, is that not relevant in this situation? I'm just confused about that. You know how it's like 0, 0, 0, 1, 1, 0, and then 1, 1?
No, I think it's very relevant. So
Okay,
if
so you
A
just-
and B are 0 and 0, you're selecting output 0. If A and B are 0, 1, you're selecting output 1. So you can use A and B as your inputs and have them represented in binary, and that will allow you to select for any one of the outputs. I don't know if that answered your question.
No, I'm just a little confused because I thought like Nand like I get what you did with De Morgan's theorem, but I thought NAND meant that like it's in the output if the two like two digits are 0.
Yeah, let's take a look.
Okay.
Suppose we write it out in longhand notation, just to sort of emphasize what's going on here. Suppose you wrote out A, B, 0, 1, right? Or A, B, 1, 0. And then instead of plus, you used times. And then the outputs were inverted. And then the whole thing is inverted. So the part over here where it's inverted, that's equivalent to this part. The part over here where it's ANDed, that's equivalent to that part. The part over here where it's inverted, that's equivalent to this part. The part over here where it's inverted, that corresponds to that part. So now let's use De Morgan's theorem, and we'll write that A prime B inverted, take the times to convert it to plus, A B prime inverted, and now invert the internals. So I inverted, and now what do I get is A prime B or B A B prime, right? Because inverted, the inversions cancel. Does it make any sense?
Yeah, and then it would be 1 and 2 because that would be equal to.
That's
okay.
where we connected it.
Yeah.
Okay. Yeah. And so this is 0, 1. That's 1, 0. And that's binary for 1 and binary for 2.
Okay. Thank you.
1 and 2. And that's that. So here's an interesting question from homework number 5. Do decoders give you all the product terms for a given function? So let's ask it again. Do decoders produce product terms? These things here, these are all product terms. Let's look at it again. See these things here? They're all product terms, and we sum them together in order to be able to create functions. So the answer is true, because yes, indeed, the decoders give you all the product terms. And you use those product terms in order to be able to create functions. So if this is M7, the product term is going to be ABC. If this is M6, then the product term is going to be ABC prime. Get it? Does it make sense? Am I making any sense? So that's question 11. Decoder produces product terms. Question 11. What do you think? Is it confusing? I'll try another one. Let's try this one. So now I got a whole different thing here. Oh my goodness, what am I going to do? I have S0, S1, S2, S3, S4, S5, S6, S7. I got A, B, and C, and this is a 3 to 8 decoder, right? And somebody took the outputs and inverted them. Oh no, what do we do? They've inverted all the outputs. And then they hooked S3, S5, and S6 all up to a Nand gate to give me a function. Gave me a function. What is the function stated in canonical sum of products form?
Would it be 3, 5, and 6?
Exactly. 3, 5, and 6. How would I write out the truth table for such a function? Any ideas? How do I fill out my truth table from the canonical sum of products in shorthand notation?
Wouldn't just 3, 5, and 6 have 1?
Exactly, exactly. So there's 3. Here's 5. Here's 6. And so the question is, given the following circuit, which of the following is true? If all 3 inputs are a logical 0, then the output F will be a 1. Is that true? The answer is no, because here all 3 inputs are a logical 0. The output is not a 1. Here's another one. It says, if 2 out of the 3 inputs are a logical 0, the output is a 1. 2 out of 3. Well, here 2 out of 3 are logical 0, and the output is not a 1. So that's not true either. But then he says, if 1 out of the 3 inputs is a logical 0, then the output is a 1. And there it is. 1 out of the 3 inputs is a logical 0. And so the output is a 1 under only those circumstances. And so what you have here is an English language statement that describes the truth table and how it functions given the circuit. So only one of the choices is correct. And that is question number 12. Question number 12. What do you think of that? Who got confused? Be honest now.
So like for that question, it was only regarding like the only outputs with 1 is if one of the like 3 inputs is 0, essentially.
Yeah, it says a 3 to 8 line decoder is connected as shown, just like the diagram I drew, only neater. And we've got these inputs, and it says here F equals 1 when. And then it gives you a list of things that could make F equal to 1. And the only thing that makes this true is if 1 out of the 3 inputs are logical 0. Now, if you said to me, let's do it again, only this time we'll do it where 2 inputs have to be logical 0. We'll make a new function and we'll call it F1. And here we see 2 inputs are logical 0. And here we see 2 inputs are logical 0. And here we see 2 inputs are logical 0. And that's it. All the rest are 1 or 0. So now I can, in principle, write out that F1 is equal to a summation of, this is row 1, That's row 2. This is row 4. Right? Totally different function. And if you want to implement that, what you could do is get yourself a little NAND gate, call it F1, and then wire it up to 1, 2, and 4. And you can see the wiring is different, the function is different, but the idea is the same. We specified the function, we created a little NAND gate, and we wired it up. We can make another function if we like. Maybe one where you have, I don't know, 3 zeros or something, or 3 ones even, or any ones. You could make an OR gate or an exclusive OR gate. That'd be good. So we've got an opportunity to make any function we like. All we have to do is specify it, write its truth table, wire it up. What do you think of that?
So essentially, you can just make any function you want, depending on like what output goes where and what gate you're attaching it to.
Exactly. Exactly. Suppose I said to you, I'm going to wire up outputs 3, 5, 6, and 7. Okay. So here's a little AND gate, and we're going to go 3, 5, 6, and now 7. So here comes, I'll call it F2, and it's equal to sigma M of 3, 5, 6, and 7. That is stated in canonical sum of products. Given the canonical sum of products for F2, find the canonical product of sums in shorthand notation. So now we can say, well, that it must be also equal to capital Pi, capital M, and what goes inside the indices?
Wouldn't it only be 0, 1, 2, and 4?
That's exactly right. Does everybody sort of see how that came about? So that works out all right. If you were going to write this out in a slightly longhand notation, it would be M0 times M1 times M2 times M4. And that works out fine. We're doing question 10 now. And isn't it interesting that if you have this, M0, M1, M2, and M4, you can write it out in longhand. Write out the binary. And then write out A, B, and C. Actually, you need the pluses in there. Oops. And now, where's the inversion going to be in the next term?
C.
That's exactly right. So now we've got it in canonical product of sums longhand notation. And if you wanted to, could you find all of the answers to question 10? And the answer is yes, you can. By the way, you know, homework 5 is available. It's up and running now. So you should be able to get in there and take a look. Suppose I leave it to you guys to ask me a question about homework 5. You guys got any questions at all about homework 5?
I'm looking at it now.
Okay. I'm going to try one with don't cares. So we'll try a minimum sum of products form given question 9, which says that F is equal to sigma M of 0, 1, 2, 9, 13, 15, sigma delta 4, 5, 11. So now I've got this really interesting thing. It says find the minimum sum of products. How do I do that? You guys can do this now, right?
We could just draw a K-map.
Yep, let's do a K-map. Only this time the K-map is going to have don't cares in it. Let's change colors. So the ones go into 0, 1, 2, 9, 13, and 15. And the don't cares go into 4, 5, and 11. And all the rest are 0. What am I going to loop? Mateo, what shall I loop?
0 and 1.
0 and 1. Well, if I did that, what about 4 and 5? Wouldn't that make things simpler?
Yeah.
So let's do that. Let's loop 0, 1, and 4 and 5. Mateo, what is the product term for that?
Wouldn't it just be C prime?
Well, we see that A is not changing and it's 0.
Oh yeah, so A prime, C prime.
There you go. That's exactly right. Let's try another one, Mateo. What else can I loop?
13, 9, 15, and 11.
Great. And what would be the product term for that one?
AD.
You got it. And you're getting it. But one more thing, it looks like I'm missing something. What should I do with this lower left thing in the corner?
Would you just loop it by itself? Or...
You could, but it would not be a simple form. What else could I loop it with?
The 0.
Yeah. And if you loop it with 0, then what's the product term?
A prime, B prime, and D prime.
Exactly right. And so now I can write it out. And that is a correct answer for question 9. So who got confused by the looping with the don't cares? Thank you, Mateo. So we've got the don't cares down now. Is it clear that you can loop around the corners here? Everybody's all right with that? Let's go back a
I got a
bit.
question.
Sure.
Why can we loop the don't cares with like the ones?
Well, we don't care about them, so we can either loop them or not. And we only loop them if they help us, and they only help us if they make our loops bigger. So we're not going to loop the don't cares if, if, for example, I'll give you an example. Suppose there was a don't care over here. I wouldn't bother looping that, except it would make it a whole lot easier for this loop right in through here, because I could loop around the corner. And then you'd have a different product term. Instead of one with 3 variables, you'd have a product term with 2 variables, and they would be B prime, C prime. You see how the don't care really helped you out? Because what you had was this, and now what you got was this, because I turned this 0 into a don't care. But because it was a 0, we assumed we cared and that it needed to remain 0. So by converting it to a don't care, I changed the problem. In other words, I converted this don't care into an 8, put the 8 in there, and by doing so, I made the problem simpler to implement, but I really changed the spec and made it incorrect. So you can't just introduce don't cares if you feel like it. You got to use the ones that are given, and then if they don't help you, you don't use them. Does that make any sense?
Yeah.
Good, good. Let's try another one with don't cares, because I think that's a very good thing. We're going to find a minimum product of sums using a canonical sum of products with don't cares. This is question number 8. So let's do question 8. I think it's a good one. We're going to write this. F is equal to sigma m of 1, 2, 4, 5, 8, 14. So this is a canonical sum of products in shorthand notation, okay? And I'll put in 6, 10, and 13 over here. And then the problem says find the minimum product of sums. Now, if it said minimum sum of products, I'm all over that, right? Because I can do a K-map. We just did that. That's easy. But now it says find the minimum product of sums. That's different. That's different. What do I do?
Don't you loop the zeros instead of the ones?
You could do that. Or what else could I do? Instead of looping zeros, what if I just said, let's find f prime? What do you suppose f prime is equal to?
Three, 7, and 15.
Yeah, including 0.
I
And we keep the don't cares just the way they are. Now what do I do?
came up.
Yeah, let's do the K-map again. Let's do the K-map again. A, B, C, D, 0, 0, 0.
Hey, Professor, wouldn't there be one more product in f prime? Wouldn't there be also 9 as well?
And 11.
Let's see. Yep. Thank you. Yep. Yep, yep, yep.
Is it 12
Zero.
too?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Thank you. Thank you. 12, 13, 14, 15. Okay. Did we get them all?
Yeah, I
Hopefully.
think so.
All right. So let's that doesn't make sense. I did it wrong. 0, 1, 2. Shoot. I got to do it again. Sorry. I numbered my K-maps wrong. Because I got to 16 and I said, hey, there can't be 16. That's not right. This is what happens when you use an iPad to do things. A, B, C, D. I'm blaming the iPad. 0, 0, 0, 1. Zero, 1, 2, 3, 4, 5, 6, 7. I'm counting out loud because I don't know how to count. 8, 9, 10, 11, 12, 13, 14, 15. Good, good, good. It ends on 15. That's what I'm looking for. So now I can fill in 0, 3, 7, 9, 11, 12, and 15. 0, 3, 7, 9, 11, 12, and 15. And then for my don't cares, I can put in 6, 10, and 13. And then for my zeros, I can fill those in. And so I should have zeros on 1, 2, 4, 5, 8, and 14. That looks right. So, Daniel, haven't talked to you in a while. Daniel, what do I loop?
You would want to loop 3 through 11.
Oh, that sounds good. All right, just a minute, please. 3 through 11. Okay. And what's that one called?
Wouldn't that just be C and D?
You got it. And what else could I loop, Daniel?
Couldn't you loop 9 and also 11 together?
You could, but you could make it simpler. How could I make it simpler?
9, 11, and 10.
Well, you can't loop 3 things. You can loop an integral power of 2.
Oh, wait, it would be 9, 11, 15, and 13 because of the...
There you go. That's it. And what is that one called?
That would just be A and D.
Yep, that's exactly right. What else can I loop? It looks like I've left something off. What about this guy? Can I loop him with anything? How about this? Can I loop him around the corner? Can I do that?
No, you can't do corners. Or
You
like,
can't do that. Nope, you
yeah,
can't. So then as a result, I've got to leave him alone. He's A, B, C, D, and all inverted. Now, what about this one here? What can I loop it with? 12. What should I loop 12 with? Daniel,
Yeah, isn't it only with 13?
Yep. And so then, Daniel, what do we call that product term?
We would just call it A and B.
Well, it's A, B, and C prime.
Oh, sorry, yeah, it's A, B, and C. Yeah, A, B, and C prime.
So knowing that, I now have determined a minimum sum of products for f prime, which is equal to A, B, C prime, or AD, or CD, or A, B, C, D, all prime. But that's not what he asked for. He said he wanted a minimum product of sums. And what did I do? I came up with a minimum sum of products for f prime. So what do I do now?
De Morgan's theorem.
De Morgan's theorem. Oh, I'm so sick of De Morgan's theorem. Oh my God. Let's go find this De Morgan guy and figure out where he lives and tip over his garbage cans. All right, we'll do De Morgan's theorem since you asked for it. A or B or C times A or D times C or D times A or B or C or D. These are all, I can't write it in one line, so I'm going to write it as F. And that is a minimum product of sums. Does everybody see what I did to get the De Morgan's theorem going? I changed the pluses to minuses. Sorry, I said plus to times, times to plus, and inverted all of the variables. Maintain my order of priority. What do you think? Did it make sense to people?
Yeah.
Yeah.
You all right? So that was question 8. Had a few steps. This is a kind of question that you will see on a test. This is a definite midterm type question. Definite midterm type question. In fact, they all are. They're, midterm could be just like this sort of thing.
I've got a question.
Sure.
Is the midterm going to be similar to the homeworks that we've been doing in a similar sort of fashion where we do multiple choice?
Yep. Midterm's going to be mashup of prior homework questions, and it'll be long.
Okay.
Maybe,
And it'll be still on Blackboard the same way we've been taking everything, right?
Yep.
Okay.
It's going to be like 100 questions, multiple choice or true false, and you get 2 stabs at it, and you'll get the best grade of the 2 attempts, and you get 2 weeks to do it. And it's open book, open notes. How's that grab you? So hopefully you'll work on your own when you do these sorts of things. And with COVID, I think it's kind of hard for people to be working together anyway. But it's essential that you do your homeworks, because when you do your homeworks, you're practicing for your midterms and your final. And in fact, the final is going to be just like the same form as the midterm, only with a more comprehensive test that uses the second half of the course. So that's the midterm. That's the plan. That's the plan. How about if we do? We need to. Did we start doing homework 5 already? I sort of recall having done this with you guys before. We did a few of these questions, didn't we? Or not?
Just today, I believe.
Just today? All right.
Yeah.
So, all right. Well, let's take a stab at one of the simple ones. Do a simple one because we got a couple or 5 minutes left. Let's do a simple one. So this is problem 1. And it says F is equal to sigma M of 1, 3, 5, 6, and 7. convert the canonical min term to a canonical max term. So then you write pi product capital M. What do you put in here? Dominic, I haven't heard from you in a while. Can you help me finish this up?
Is it 0, 2, 4?
That's exactly right. That's exactly right, Dominic. You're doing fine. Doing fine. Does everybody see what Dominic just did? Form the complement of the expression. You could write this out in longhand, M0 times M2 times M4. And if you put it in the binary, oops. What would you write? This is supposed to be a product of sums, so you need plus signs in here. So where did the inversions go? Dominic, any idea?
First part A, B, and C. Second part A and C, and third part B and C.
You're close. You want to invert only where there's a 1.
Oh,
Because
okay.
it's a product of sums instead of a sum of products. It would be exactly right if it was a sum of products. Then it would be A, B, C, A, B, C, A, B, C. And what you'd get is F prime because you're using the complement set. And then you'd have prime, 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 or prime, prime, or prime, prime. And it's
Gotcha.
clear, right? Because F prime is equal to, in sum of products form, 0, 2, 4. That's F prime. Right? In other words, it's the complement of the set. So if you look at the set of numbers, 0, 2, 4, 1, 3, 5, 6, and 7. Here's the whole set. Here's the subset. And this is the complement of that subset. And so if this makes it positive, then this will make it negative. So that's how that works. Well, look, it's 3:13. We got till 3:15. I got 3:13 and 34 seconds. So I'm thinking we're going to call it quits for the day. You got some reading here. I'm going to make sure that you guys are assigned the correct reading. So you're in chapter 4. That's where we're at. We're reading right up to, but not including, page 194. You got to keep up with the reading on this one because, I don't know, it's kind of heavy duty. And what you're going to do is you're going to read from the beginning of chapter 4 all the way up to page 194. So let me just get a page number for you on that. It's page 160. So that's some reading. You guys got to keep up with the reading. Everybody should have a book. Does anybody need a book? Everybody has a book? Okay. I'm hoping everybody has a book. Well, look, it's snowing out, so if you're going to drive, drive safe. Otherwise, stay home and stay warm. And thank you for your attentions. Have a nice weekend.
Thank you. Ethan.
You too. Thank you.
Thank you. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.